it. Now let's see from where we define these rules and how did we configure these rules. For that purpose, DFMPro provides Rule Manager. I can invoke the DFMPro Rule Manager from toolbar or menu, or I can just choose to edit the existing rule file by pressing the edit button. Let's do that. Here, the DFMPro Rule Manager lists all the available rules that are there against which the design is checked. I can group them by the category. For each of the applicable category, I can choose what are the rules that I want to run or which rules I don't want to run. Again, for each of the rule, I can configure their parameters. So for example, the defaults, I can exactly define what do I mean by the defaults. So I can specify that depth to diameter ratio should be less than the value of 8. I can also define what is the criticality of this rule in my context, whether it's really critical or probably I can put it at a medium level of a violation. Once I configure the parameter, I can save the rule file by different names. So for example, I have one vendor with certain process capabilities, whereas I have another vendor who may be able to handle much better machining parameters. So in that case, I can create the different standard files for different vendors, and then I can validate the design against a specific standard file based on which vendor or which machine shop I am going to give it to. Just now we saw the example of the milling. Let's see example of the sheet metal fabrication validation for the manufacturability. Here again I have a part. Now I'll go and choose the method as a sheet metal and simply press run button. Here again tool does the same. It tries to analyze what would be the steps of manufacturing this sheet metal part, and each of the step what could be the anticipated problem. It would come out with the list of such issues again in the task manager panel, where I can see the various categories. So for example, the first violation says that counterbore hold distance to the part edge. Again, as soon as I click on the instance, I see the relevant geometry highlighted as well as the feature highlighted. I can zoom to that particular region, and tooltip again explains me in terms of parameters as what has been violated. So here the distance between hole edge and the edge of the part is expected to be at least 4 times of the sheet metal thickness, whereas in this case it's again a very low value of 2.1 times of the sheet metal thickness. I can see the relevant counterbore feature is also highlighted in the tree, so that I can just go to that feature and move the center of the hole away from the part edge to fix this. To take one more example, here it says that open hem. So the tooltip again explains me what is the parameters which has been violated. So here it says that for this open hem, the radius to the sheet metal thickness ratio is expected to be greater than 0.5, but in this case it's less than that. I can again right click the invoke the help to understand what are the various parameters, what is the expected values and things like that. Let's see one more example, minimum hold distance. Again I can zoom to that region. Here it says that the distance between the edges of the hole should be at least 15 mm, whereas in this case it's again less than 10 mm, which could be a problem during the manufacturing process. Let's see a couple of more examples. Again I can choose the method for analysis as a turn, press run button. It asks me for the reference face to determine the turn axis. I can go ahead with the default selection. Here the first rule says the presence of non-standard hole sizes. I can click on an instance and tooltip will show me the size of the hole and nearest available lower and higher standard drill bit sizes. So as a designer, I can modify this hole to match with any of the standard drill sizes. Let's see another example of key wedge should be radius at the end. I can click on an instance, the relevant geometry is highlighted. I can zoom to that region. Here again, I can right click and invoke the help to understand this issue in more detail. Key wedges are typically manufactured using end milling cutter or slotting cutter tool. Both these tools make it impossible to manufacture the sharp key wedges. So it's always recommended that key wedge should be radius, either in horizontal plane if end milling cutter is to be used, or in vertical plane if slotting cutter tool is to be used. This kind of feedback helps designer to make the geometry correct for the manufacturing process. Let's see one more example. Minimum internal corner radius. Here again, this corner, as we can see, is making a sharp 90-degree angle. Such corners are difficult to manufacture by the turning operation. The turning tool typically has a relief provided at its tip, and the minimum internal corner radius should match with that relief. Let's see another part for the manufacturing tolerance capability analysis. So here, design engineer has used the SolidWorks Swift technology and come out with the Swift tolerance stack analysis. Now output of this tolerance stack will validate against the manufacturing process capability, whether the manufacturing process can really manufacture to that level of tolerance. I can expand the linear and angular tolerance issue. I can see that there are two instances which are flagged as a violation. If I click on the instance, the relevant dimension is highlighted and tooltip says that the tolerance here specified is tighter than the manufacturing process capability tolerance, which is like 0.25 mm. Now design engineer has the two choices. Either he goes for the output which matches with the manufacturing process capability, or if this tolerance is a design level constraint, then ask manufacturing to go to the more precision shop where probably this part can be get manufactured. But in this case it would become a conscious decision rather than an uninformed decision. I can also click on second instance and I can see the second dimension value where this tolerance is tighter than the process capability.